Okay, Lecture 9, Chemical Equilibrium. So a new subject here, so you should know that term. What happens to the concentration of reactants and products as the reaction approaches equilibrium? So let's use a reaction. This one comes up a lot. It's just a really good one because it's not all ones for the coefficients. It has two reactants and it has two products, so it's fairly complex. So we'll be using this a few times. Now, what happens to the concentrations as we approach equilibrium? So we have a reaction that goes forward. The reactants become products, but then the products then react and go back to reactants. And that's why we have this double arrow here to indicate that we have a forward and reverse reaction. But when we consider the reaction to have come to an end, it's because the forward and reverse rates have become equal, and even though reactants and products are still being made, it appears to have come to a stop for us at the laboratory level. So let's look at first equilibrium from the point of view of concentrations. So we'll have, and we'll just say moles of stuff. We'll just won't go any further than that, just in moles. That can be for reactants or products, and we'll say this is 1 mole, 2 moles, 3 moles, 0 moles down here, and then time, the time of the reaction as it goes forward. So let's say we start out with 1 mole of CO. So it starts out at 1 mole and then it drops away. So this is CO, or moles of CO. The hydrogen, let's say we have 1 mole of CO and 3 moles of H2. I just picked those. It could be anything, but we'll stick with something that is actually in the same ratio of whole numbers as the coefficients. So this drops down, so the H2 would then drop like that. So this would be H2. So moles of H2 drop away as time goes on, and this should level out. And then methane and water start out at 0, and they both go up, and they max out. So this is moles of CH4 equals moles of water. Since it's 1 to 1, they start out at 0, and then so they're going to build up at the same rate. But ultimately what we're looking at here, we have some numbers and that's fine, but what we're looking at is that eventually the moles of hydrogen remain constant, the moles of CO remain constant, the moles of methane and water remain constant. And when that happens, we have reached the end of the reaction, and also we've reached equilibrium. So if we were to map this out over time, once we reach this point, these just extend on forever at the same, as long as the temperature and pressure don't change, nothing else changes for the reaction, those moles of reactants and products will remain the same forever. So we've hit equilibrium there. So what happens for the concentrations of reactants and products? The reactants concentrations drop away. The number of moles per liter drop away for reactants. The moles per liter for the products increase, but eventually they all reach a steady state. They don't necessarily have to be equal to each other, but they have to reach a steady amount that never changes after that point. All right. Now what happens to the rates of reaction? Let's get down here. Rates of reaction of reactants and products as the reaction approaches equilibrium. So this is a different thing. Still time on the bottom here. And then we'll just say this side is rate. It can be the forward rate or the reverse rate, sorry. So we don't put any other than 0 here. We don't put anything for the rate or the time. For the reaction, for the reactants, so this would be rate for reactants. So this is the forward reaction rate of reactants. Starts out very high and then slowly drops off. Well, it actually can quickly drop off, and then eventually it hits a steady state. The forward rate is still going on. Now the reverse rate starts out at 0 because there are no products. So we had, what did we pick? CO2 or CO and hydrogen react together to form methane and water. So first there's no methane and water, but once I might as well write it in here. Forget the phases just to move along. So at first there's only CO and hydrogen normally. And so their rate is very high because that's all that's present and there's a lot of it. As they react together though, we're using them up. So they find it harder and harder to find each other. So since they can't find each other as quickly, their rate has to drop. And not only that, there's more products that are present that are getting in the way. So we start out really high for the reactants, then it drops off. For the products, it starts out at 0 because there are no products at first. But as we increase the amount, as the reaction goes forward, it goes to the right, we create methane and water, they start finding each other, and then the reverse reaction starts to take place. So it starts out at 0, nothing's happening, then it keeps creeping up because we keep making more and more methane and water, and then eventually the forward, so the rate for products, so this is the forward and reverse. When those two rates are equal, then we've reached equilibrium. And once you've reached that, then you can't break away from it. You have the forward and the reverse rates are equal, then there's no way for them to get ahead of each other because as they're exactly the same but just going in opposite directions. But the important thing here is that we reach the equilibrium and that it's dynamic. The forward reaction and the reverse reaction keep happening. Even though we look at the reaction as if it's done, if we were looking at this in the lab, we'd just say, well, everything stopped, but if we looked on the microscopic level, we'd still see methane and water being formed and CO and hydrogen being formed. And it just goes on. You know, they're every bit as dynamic as they were before the reaction ended. So it's a little different than we think of when we're looking at it from the macroscopic point of view. Okay, let's look at our first problem here. Consider the reaction, that's reaction, RxN, CO, same reaction. As I said, it's just a really great one to work with. We'll have some other ones in here too. So 2.5 moles of CO and 10 moles of H2 are placed in a 10-liter reaction vessel at 651 Kelvin. At equilibrium, there is 0.5 moles of methane present. What is the molar composition? And in this case, they mean number of moles. And I'll make that clear on the exam. I'll say how many moles of each thing is present at equilibrium. So what we do is we use, what I'm going to do, I'm write the reaction below here. And we got plenty of room. You can see up here, I didn't change this one around, but that stands for that arrow. I did later. I finally found a double arrow that I liked for a word. Actually, I had to make it, but so if you ever see this on the exam, it means the same thing. It's just easier to write. Let's write this reaction out. Now we're going to use the ICE table. Initial, change, equilibrium. So they say at equilibrium, now we're going to just use moles because that's what they're after. They just want number of moles. They give us the 10 liters here, so we can divide moles by liters to get concentration. Concentration is generally what we're going to be after, but here we're not talking about Kc. Kc, the equilibrium constant is in terms of concentration. Here it's just moles, so we'll leave it as moles. So this is the first and the easiest of the problems. Feel free, if you get used to concentrations, which you should, you can use concentrations to solve this, but when you're done, you're going to just have to convert back to moles. If this is the first problem you're seeing, this won't make a lot of sense, but when we go on and on into these problems and you see them in the book and in the lecture, you're going to know these like the back of your hand. So when we have, I'm going to approach it as if you haven't seen this before. So we have the initial number of moles are given, and when they don't say anything about the products, they must be 0. That's normally the case. If they want to tell us that there's some moles of product, they'd have to mention it. Now the change here, we don't know. We know that there was a change. The reaction did go forward, so we put minus x. We don't know what x is, but we know that we lost some. This might be minus 1 to indicate, so that we add them up. Is 2.5 minus 1 will be 1.5. But we don't know what it is. We just know that it's is negative because we lost some and we put x. Now this one would be minus 3x because we have to go with the stoichiometry of the reaction 1 to 3. So for every x that we lose of CO, we must lose 3x of hydrogen. We must gain x here and gain x here, 1 to 1. So we have to learn to use those equations. Now at equilibrium, that means we had 2.5 moles minus x. I'm going to leave off the units. That's generally what I'm going to do when I come down. These are definitely moles, but I'd have to put it in either moles next to each of these or put it in parentheses and put moles. It can get a little nasty. Since we have it up here, we know that we've carried it through. And then they say at equilibrium there's 0.5 moles of methane. Well, the methane that we have at equilibrium, that's what this bottom line is. They said that methane, we have 0.5 moles. Well, we also know that we have x, so x must be equal to 0.5 moles. So since we know what x is now, we can carry it through here. We can see that we end up with 2.0 moles of CO. If we put 0.5 into this, we end up with 8.5 moles of hydrogen. Got to have that 3 in there, and then we know that we have 0.5 moles of methane, because that's what they told us, and it must be the same for water. So we can use it's not by chance that they ended up the same, the methane and the water. Sorry. It's because they have the same coefficient here, 1 to 1. They both started at 0, so they both have to add in the same number of moles. And so we end up here. I should say one thing, these problems can get pretty lengthy, so I may get off the page and may have to go back up, so I'll go back and forth. So you might want to write some of this stuff down or just replay the video to look at the original values if you get lost. Okay, and I just want to check one thing here. Yep. Okay, let's try another one here. So one of the basic problems that you may face on the exam, this is part B, so it's the same reaction. I'm going to write it again. And I'm going to leave off the phases this time just to keep moving. Now that should have the phases in there, but if you're solving this on the exam, I'm not going to stop you. You'll be upset if you do that. If the answer requires a phase, yeah, you definitely want to put that in. All right, so initially we have 4.5 moles of CO. That's what it says. We have 3 moles of hydrogen, and we have 2 moles of methane. That's what we start with, and it doesn't say anything about water, so this must be 0. So this is different because we've started with a certain amount of product. But remember, these are reversible reactions, so they go in either direction, so there's no reason we can't start out with some products. You can make the reaction vessel contain whatever you want at the start. Then we let the reaction go, and they want to know how much. We know that there's 0.15 moles of water vapor present at equilibrium. So the change is minus x, minus 3x. That 3 is desperately important. You need to have that in there, plus x. If this was 2 waters, it'd be plus 2x, but it's just 1. So look at the coefficients. If this was 5 and this was 7, this would be plus 5x, plus 7x. Don't forget to put these guys in, but since they're 1 to 1, it's just plus x, plus x. And that's should say that's one of the problems that we deal with. I mean, there's an infinite number of these that we could create. Any reaction can be used here, so any coefficients can be used, and it can get throw people off because I can only do so many types. I'm going to do 3 here. You have several in the book. I'll do 2 or 3 in class. Even with 10 or so or 15 that you can look at, there's still many other types that we haven't covered. So you got to get used to the basic idea rather than hoping to see this exact equation on the exam. It most likely won't happen. So they say at equilibrium, so here's at equilibrium we have 0.15 moles of water. So that's equal to x. So once we know x, then we just plug everything in. X goes into each of these equations. So we end up with 4.35 moles of CO. It's 4.5 minus, let me make sure. And then we have 3 times 0.15 plus 3, and we end up with 2.55 moles of hydrogen. And then we end up with 2.15 moles of methane. And then they gave us 0.15 moles of water. Now, as far as the rules for significant figures, as I'm adding and subtracting here, they might not quite match up. Just give me three significant figures back, and that's all you have to do. Let's try one last one. This one's a little different from the others. 5 moles of each species. Same reaction, by the way. I'm going to try to write larger here. And initial change equilibrium, same as before. Now, they said that we have 5 moles of each species is placed in the same vessel at equilibrium. And so they said of each species, so there's 5 moles here, 5 moles here, 5 moles here, 5 moles here. And they say, this is going to be minus x, minus 3x. So the reaction starts out this way. We lose some reactant, we gain some product, and then we end up with 5 minus x. Again, I'll leave off the units. We know what they are, just to clear up some space here, especially for this one, we'll need it. And then they say, at equilibrium, we find that there is 4.20 moles of CO. Well, at equilibrium, we have 5 minus x CO. So these are equal to each other. So we're given, we set up the equation, or we set up the table with variables, and then they tell us what CO actually is. So x is going to be 0.8 moles when you solve for it. And I've gone back and forth with the idea of putting in every step of the calculations, but at this level you need to be able to take this equation and solve for x without me doing everything out for you. It's just going to take up a lot of time. So if there's ever a question, of course, ask me. But now x is given here, so but that's not the answer. That's not the answer to any of these now, because what they want are the moles of each species. Well, that means it's 4.2 moles for CO. We were given that. And then we have 0.8 times 3 plus 5. So we have 2.6 moles of hydrogen. Then we have 5.8 moles of methane and 5.8 moles of water. Because we didn't start with anything that was 0 on this side, x is not the actual answer. It's the last step before we find the moles. If I've been saying concentration, sorry about that, but it's number of moles in this case. So and I say concentration. If I did, it's because we 90% of the time, 95% of the time, we use concentrations. That'll be the next set of problems that we do. But here, if they ask for moles, you got to give them moles.